All right, today we're starting section 2.1, and we're going to start our discussion of the derivative. Specifically, this section is going to look at derivatives from an algebraic standpoint, and we're also going to talk about the tangent line problem as a connection to that. So looking at this first, we're going to take a look at something we have seen before. We saw it back in section 1.1, and it's called the tangent line problem. And what it does is it actually shows us where this concept is coming from. So we talked about secant lines and tangent lines. Nod your head if you remember talking about this. Okay, that's good. And what we did is we said that if we had a graph, and I'm going to draw the exact same graph twice. So a secant line is taking 2 points on our curve and connecting them with a line. We will call one point C, and the other one we'll call C plus H. And that means that over here, this first point is F of C, and this little bit higher point right here would be F of C plus H. And if I were to want to find the slope of this line, what I would do is I would do the change in y over the change in x, right? So what we see down here is that description. The slope of the secant line is the y value, the higher y value is what it's using here, f of c plus h, minus the lower y value, f of c, and then it's pairing up the corresponding x values that go with it, c plus h and c. The denominator simplifies to just give you h, so we get f of c plus h minus f of c over h. That's the slope of a secant line. Okay? What we want to do is we want to take those same 2 points. I should have started with the graph actually already having those on there too. Try to get them about the same. Those same 2 points. And instead of finding the line between those 2 points, we actually want to have the 2 points get closer together. Okay? So instead of this location, right, we'll shift it to over here. As our central point. We're going to allow this point to get closer here. So now it's going to be right here. And then it's going to get a little bit closer here. And so now it's going to be right here. And it gets closer and closer and closer to the point in question, whichever point it is. And we could have done it equally for that first point I noted instead of the second point. And that process is a limiting process, right? We're letting the gap between them get infinitely small. Another way to say that is we're letting h, that's the space between them, approach 0. So that's actually the slope of the tangent line that we're talking about. So f is defined in an open interval containing c. We saw that happen, right? It's got to be defined, so no holes, no gaps, no asymptotes. Then if we take the limit as h goes to 0 of that same slope that we found on the previous slide, f of c plus h minus f of c over h, this equals m, and this value will exist. The line passing through c f of c with slope m is called the tangent line to the graph of f at that point. The slope of the tangent line to the graph of f at that point is also called the slope of the graph. So what we're seeing is we're seeing several pieces of vocabulary that all mean the same thing. I'm going to underline, well actually I'll highlight them. Slope of the tangent line, slope of the graph, and in a little bit, we're also going to call this the derivative. And all of these words mean the same thing. They mean this definition that has this limit in it as h goes to 0. Out of curiosity, how many of you have had some calculus exposure in the past? Okay, so maybe about a third to a half of you have. There are processes that are easier to work with than what we're going to do in this section, okay? We'll get to them in 2.2, so it's going to happen next week. But what I want you to understand is that in order to get to those processes, you have to understand the background behind them. Like, why does it work? Why does it make sense? Because they didn't just come out of nowhere. People developed those based upon this limit definition. So we're going to spend a little bit of time working with this limit definition of derivative. All right, so the first example is that we're going to find the slope of the tangent line to the graph of the function at the given point. So they give us the point 1, 5. Okay? So when we're taking a look at doing this, we've got the limit as h goes to 0 of, and I'm just writing down what it is on this from the previous slide, f of c plus h minus f of c over h. This is our definition. And the c value and the f of c plus h value, it's the 1, 5. Right, that's what we're working with. We're working with the 1, 5. Have all my pieces there? I think so. Okay. The problem is that that's just one of our points, right? This point is the x and the y pair of c, not c plus h. We have to let h be a little bit different of a value. So as we're looking at c plus h, what we're actually, let me put the c's in as 5s so you can see this happen. I'll show you another way to do this in a moment too. So c is 5, so this is 5 plus h minus f of 5, not 5, sorry, I meant 1. I am so sorry. This is 1. And then f of 1 over h. Okay, c is 1. That's coming from this. So put the 1s in everywhere. Well, f of 1 means the y value at 1, and I know that. The y value at 1 is 5. Okay, is that okay so far? We're just putting in the 1 and the 5 in the locations where they apply. But we need to figure out what is f of 1 plus h. Well, that goes back to the equation that we were given. The equation we were given is 6 minus x squared. So if I want to find f of 1 plus h, which is what I'm looking for, I need to put 1 plus h in for the x. So this would be 6 minus, and it's 1 plus h squared. And I got to do a little bit of algebra, distribute FOIL, multiply that out, and find out what I have. So this is 6 minus. So remember, 1 plus h squared means 1 plus h times 1 plus h. Don't go squaring the pieces and think you're done. You wouldn't be. If I multiply this out, I have 1. On the inside, I have h, and on the outside, I have h. That's 2h. And on the last piece, I have h squared. And then I would distribute. So this is 6 minus 1 minus 2h minus h squared. And the 6 minus 1, of course, is 5. So all this work over here tells me what f of 1 plus h is, and that's what's going to go right here. That's f of 1 plus h. So back over here in the problem that I'm working with, where the whole problem is present, I'm going to write 5 minus 2h minus h squared. I have then minus 5, and I have it over h. What do you notice happens with the 5s?
They cancel out.
Yeah, there's a positive 5 at the beginning, and there's a negative 5 at the end. Those are 0, then when we add them together, right? And everything in the numerator has an h in it. So I'm going to do one step that you may not need to see, but I'll do it for now anyway. What I'm truly doing is I'm factoring h out of the numerator, which leaves me with negative 2 and minus h divided by h, which allows me to cancel those two h's. We worked with limits in the last section. Let me shrink this just a little bit. So I'm left with the negative 2 and the minus h. And up until this point, I couldn't let h be 0 because we would have a 0 in the denominator. But at the point when the h in the denominator is able to reduce with an h in the numerator because it factored out, now I can let h be 0. So this is negative 2 minus 0, or just negative 2. Now that's okay, but it's very specific. It was very specifically only for the 0.15, right? It doesn't tell you what would happen if I'd had like 2. What if x is 2? What if x is 7? Well, this doesn't really give you any information if it's those values, correct? Okay, So I want to adjust what we've done on this particular problem. I'll do it on the right-hand side just by deleting this part on the right-hand side for now, to do it more generally for x instead of doing it specifically for 1. Okay? So instead of using c's where the c's are, I'm just going to use x. So we're going to do the limit as h goes to 0 of f of x plus h minus f of x over h. And what I'd like to show you is that there's really 4 steps or 4 parts to doing this problem. So I'm going to break it down into 4 pieces, and I'll use a highlighter to try to show you what the pieces are. One step is the step that I just erased underneath this one, right? It's that part that has the plus h in it. So we're going to call that step 1. So in step 1, we're going to find f of x plus h. And I'm going to show you the steps as we do them. Okay? Well, our problem over there was 6 minus x squared, yes? So we've got 6 minus, and it's not going to be x squared, it's going to be x plus h squared. So that's what it means to put in x plus h, right? We do the same algebra that I erased from underneath here, but we do it generally for x plus h. So if I multiply x plus h times x plus h, and I FOIL that out, I get x squared. On the inside and the outside, I have xh, so that's 2xh. And my last term is just h squared. And if I distribute the negative, this is 6 minus x squared minus 2xh minus h squared. That's step 1, and it is the hardest step. It's the step that expands things and makes something bigger. Every other step we do is going to condense things and make them smaller. Okay, step 1 is going to be the most massive step you have. Step 2, I'll highlight that in blue. I said blue, and then I changed it. All right. So step 2 is to do the entire numerator. So step number 2 is to take that f of x plus h that I just got from step number 1 and to subtract off f of x. Okay, well, f of x plus h was step 1. It's this one. So I have 6 minus x squared minus 2xh minus h squared. And then I'm going to subtract f of x as it was originally given to me. And I'm going to put in parentheses as well, this is 6 minus x squared. That is. I like putting the second piece in parentheses, and here's why. Everything in that f of x is going to cancel out. It's going to cancel out with something over here. So if I isolate it back here, I can see all the pieces going away very quickly. I don't have to distribute negatives or anything like that. Because notice what would happen if I do. If I distribute this negative through and get negative 6, the negative 6 will cancel with the 6. And if I distribute the negative through and I get the positive x squared is going to cancel with the negative x squared. All the pieces are going to fall out. So this piece falls out with this piece, and this piece falls out with this piece, and it's reduced. I have fewer terms than I had in the previous step. Now I only have 2xh and minus h squared. Right, condensed. That's step 3. Going back to our original equation, step 4 is now all of it with the fraction, so I'm going to do the dividing by h part. I will highlight that in green. So I have the dividing by h. So I'm just going to identify that. So step 3 is to divide by h. So I take what I did in step 2, what remains, which is negative 2xh and minus h squared, and I divide by h. And just like when I was working with this over here, what we should notice in this step is that the h will be able to reduce. If the h is not able to reduce, it means I'm never going to be able to plug 0 in. Right? So it will be able to reduce. I will pull the h out of the numerator. So I have negative 2x and minus h over h. And lo and behold, what happens to the h's? They cancel. this to shrink just a little bit. Okay, it's going to shrink my line in the middle of it. That's okay. All right, last step. The last step, I'll do it in purple, is the limit part. So the last step is to take the limit. I should have said step 4 first. My apologies. Let's do that. Step 4 is the limit. So I take the limit as h goes to 0 of what remains from step 3, right? Everything's building on it. So step 2 relies on what you did in step 1. Step 3 relies on what you got in step 2, and step 4 relies on what you got in step 3. So step 3, I had left the 2x and then minus h from here, right? Now I can put the h as 0 in, and I get negative 2x. Now you might be saying, but the last problem I got negative 2, right, the other way I did it, and this time I got negative 2x. What gives? Well, I just need to do one more thing. What is x in this problem? It's 1. It was given to me at the beginning. So the last thing I have to do is to go back up here and to recognize that I was given, that was a big enough circle, wouldn't it? I was given that c, or x, is equal to 1. So at the very end, I let x equal 1, because that was what I was given, right? So this one gives me negative 2. This is called the 4-step method. If you choose to use this, you need to make sure you label the 4 steps. Okay, what we don't want is we don't want it to look like step 1 is equal to step 2. It's not. Step 1 uses the information, step 2 uses the information from step 1, but it's not equal to step 1, right? It's another step with additional information plugged in. I will show it with the 4-step method. I think it keeps things organized pretty well. If you don't like that and you'd rather do it more like we did the first go around, you can do that too. Neither way is wrong. So this is what I actually was using at the very end there. I was using the definition of derivative for a general location of x instead of a specific location where I've got a numerical value c given, like c equal 1. So the derivative of f at x has a notation now. That notation is a prime notation. So it's f prime of x. There's a couple other notations we'll encounter later, but for now, that's enough. And you see the notation over here looking just like the other pieces with x's instead of c's. And also looking just like the version of the problem I just did. F of x plus h minus f of x over h. This works provided the limit exists, and for all x for which this limit exists, f prime is a function of x. So the first example we did was a polynomial, right? This is a polynomial. So I'm going to show you a couple other types of problems that aren't polynomials because they don't simplify algebraically in quite the same way, which should make sense because they're not all polynomials. So the next one that we're going to do is called a rational function. So this one I don't have, x squared plus x plus 7 or something like that. I've got an x, in this case, in the denominator. Now, there are clearly places where this one won't have a derivative. Where will this not have a derivative? Where is it not defined? Yeah, 0, right? X can't be 0. So this definition only holds for the values for x for which it's defined. It's not defined here for x is equal to 0. So if we're talking about at x equals 0, it just doesn't work because it doesn't fit the definition. So what we're working on this, we're going to work for all of those other values for which it is defined. All right, so we're going to write down our, I'll write it at the top first. What we're finding, is f prime of x. It's the limit as h approaches 0 of f of x plus h minus f of x over h. And the steps are the pieces going in order. So step 1. Step 1 is to find f of x plus h. So I replace x with x plus h. Technically, that's all of step 1, but since I know I'm going to have to be working this out later in step 2, I'm going to go ahead and simplify what I have. I've already multiplied x plus h out twice, at least a version of it today. So eventually, right, you work something out enough times, you don't have to work it out every time because you just know what it's going to be. This should be 1 over x squared plus 2xh plus h squared. That's what happens if you FOIL that out or distribute that out. So that's step 1, just the version of it sort of like, not reduced, but expanded out or multiplied out. That's step 1. So step 2 is the entire numerator. So step 2 takes what I did in step 1, that is f of x plus h, and it subtracts off the f of x that I was given at the original part of the problem. So this is 1 over x squared plus 2xh plus h squared. That's f of x plus h from step 1. And then minus 1 over x squared because that's f of x. Now, you may not be a fan of fractions. I have several children in my house who are not fans of fractions. But you probably remember that in order to combine fractions with addition and subtraction, what has to match? The denominators. And right now they don't, right? They don't match. So what do we have to do to get them to match? Well, we have to incorporate everything that's a factor into both pieces. And since they don't have any factors that match, right? They have some terms that match, right? X squared is a term that matches, but that's not a factor. Factors mean multiplied like multiplied pieces, right? They don't have that. That means we have to multiply them by one another. So the first denominator gets multiplied by x squared. And the second denominator gets multiplied by x squared plus 2xh plus h squared. And also, you'll remember from fractions, whatever you do to the denominator, you must also do to the numerator, right? Okay, so this is the algebra that we're going to be doing on this one. Got to get common denominators. So we multiply this out. So the top becomes x squared. The denominators are going to match now, and I'm going to leave them in this sort of ugly factored form. You'll see why in a moment. I don't really want to distribute that out. That would be extremely unhelpful. Okay, so it's going to look like the two denominators just multiplied. Okay, the first numerator is just going to be x squared now. And then I have the subtraction right here from the middle. And then the second numerator is going to be the x squared plus 2xh plus h squared. Notice I put it in parentheses because the negative in front applies to all of those pieces. You're welcome to distribute the negative through if you wish at this point. You're going to have to distribute it to some of the pieces later anyway. But you might notice that the x squared here is going to cancel with the x squared here because they're going to have opposite signs when you do distribute. And it's at this point that I'll go ahead and distribute the negative through after that. So now I have negative x squared, not x squared, excuse me, 2xh, and negative h squared. And my denominator remains ugly. X squared plus 2xh plus h squared times x squared as such. Okay, everybody good so far? There's nothing else I can do to clean this up. So it's step 2 that's the messiest in this process because I had to expand some things, get a common denominator. Everything after this step 2 is going to reduce things down, not significantly at first, but they will collapse. So step 3, what was step 3? So step 3 is to divide by h. So I take what I did in step 2 and I divide by h. But I'll tell you what, I don't like writing division of fractions as a fraction divided by something else. That's not particularly pretty looking. So instead of writing it that way, what I'm going to do, is I'm going to include that new h that I'm dividing by in the denominator. And the reason I can do that is because dividing by h is the same as multiplying by the reciprocal 1 over h. So in some sense, I'm really doing this, right? My numerator left an h out. There's an h there missing. Sorry about that. Okay. All good? Now, we already know that the piece at the beginning, because we already talked about it, that it doesn't reduce any. But once I put the h over here as part of the denominator, now it will. Because much like the last problem, do you see the h that can be factored out of that numerator? Yeah? So that's what we're going to do as our next step. So we're going to take the numerator and we're going to pull an h out. So now I have h, I have negative 2x, and I have negative h. On the denominator, I still have x squared plus 2xh plus h squared times x squared and times h. And this h will now cancel with this h. So it doesn't really look like it canceled and cleaned up a whole heck of a lot. It really doesn't. It just looks like, okay, so a little bit of the h's went away. I've still kind of got a mess. But our step 4 actually will help finish that off. All right, so step 4, we'll write it over here, is what? Right, it's the limit step. So we're going to take the limit of what remains. So this is the limit as h goes to 0 of negative 2x minus h on top, and then x plus x squared plus 2xh plus h squared and x squared on bottom. Now, while it might feel like, well, I still can't plug the h equals 0 in, you can. Remember, the goal is to see whether or not putting a 0 in a location or any value into a location actually creates 0 in the denominator, and it won't. So when I put 0 in, this piece will become 0, this piece will become 0, and this piece will become 0. Agreed? All those will 0 out. That's going to leave me with negative 2x on top, x squared on bottom, and another x squared on bottom. That's way better than it was before, is it not? It is, but there's still one more thing that will reduce. What do you notice? What's that?
Take an x out.
You can take an x out, yeah. The x in the numerator will reduce with, I don't care which one you want to do it with, but one of the x squareds in the denominator to create an x to the power 1. This ends up giving me negative 2 on top and x cubed on bottom. And what was the name of our function? F of x. So this is f prime of x. So when we're working with rational functions, it's going to feel a lot like that. Have to get common denominators. Now notice on this one, they didn't give us a value for x at the end, so I don't have to plug in an x equal 1 like I did last time. It's just not part of this particular problem. Okay, let's take a look at another one. This is going to feel like something we did back in chapter 1 as well. It's got an extra step here that says find an, well, not an extra step. The directions are slightly different. It says find an equation of a tangent line. So the equation of a line, one of them is y equal mx plus b, right? That's a line you're familiar with. And you can use that, and there's nothing wrong with it. But the one that's a bit more helpful for what we're about to do is y minus y1 equals m times x minus x1. So that's the one that I'm going to go with as I work with this. In order to have an equation of a line, right, a line, we have to have a slope and we have to have a point. Agreed? Or we would have to have a slope and a y-intercept specifically. They give us the point. That's why I like using the point-slope form instead of the y-intercept form, is because it fits nicer into what I'm given usually. So I have a point. I mean, y is going to be 1, x is going to be 1, y1 is going to be 1, x1 is going to be 1. That's going to be just very, very fine, no problem. But I need to find the slope, m. And the slope, m, is the slope of the tangent line, which is the slope of the curve at the point, which is the derivative, which is what we've been doing. So we're going to find the derivative, and we're going to figure out what the value is at 1. So in some sense, it's kind of like I'm going back to this problem right here. I'm finding the derivative at a point, and the point happens to be the point 1 again. So we're going to take the derivative. So step 1 is f of x plus h. The algebra for this is a lot cleaner, so I have square root of x plus h. And there's nothing to simplify. Step 2, is to take that f of x plus h and subtract f of x. So that's the x plus h in the square root, and then the original f of x was just the square root of x. Again, there's no simplifying. You might be like, well, there's something coming up because there's a radical involved. And you're right, there is something coming up, but it's not there yet. What's step 3? Divide by h. And we run into sort of a problem, right? We have the square root of x plus h minus the square root of x over h. But we saw problems like this and did limits like this back in chapter 1. And when we saw them and when we did them, we used something called the conjugate. And we're going to use that again. Okay, so we want to rationalize the numerator because we want the h to cancel in the denominator. That's why we're doing it. So my numerator's conjugate pair for that would be the square root of x plus h plus the square root of x. And I've got to do it both on the top and the bottom. Now again, I don't really want to distribute the denominator out. That's not helpful. But the numerator condenses nicely because that's the whole point in doing this, right? When I multiply the first two terms together, I get x plus h. The inner and the outer terms, right, hang on. I didn't mean to move that, I meant to cut it. Doing the inner terms and doing the outer terms, they give me the same thing but opposite signs, so they add to 0, right? That's the whole point. And then the last terms multiplied give me an x, the square root of x times the square root of x is x. And it's a negative because one sign's positive, the other one's negative. The denominator will stay written as it already is in factored form. What do you notice happens in the numerator now? Don't ever say it at once. Thank you very much. Yes, the x's cancel, right? And then the h, because that's the only thing that's left, right? There's an h on top, there's an h on bottom. Those are going to cancel as well. And when those cancel, of course, they reduce to the number 1, right? So I have a 1 on top that remains. So after all of this is said and done, actually, let me put it over here so I have some more space. I have a 1 on top, and I have the square root of x plus h plus the square root of x on bottom. That's what remains in step 3. What's step 4? Step 4 is to take the limit. So the limit as h goes to 0 of 1 over the square root of x plus h plus the square root of x. And so this one will go to 0, right? It will eliminate itself. I shouldn't be using x's maybe, but just I'll mark it out like that. So I end up with 1 over, and I have the square root of x plus the square root of x, which is otherwise known as 2 square roots of x, right? Square root of x and square root of x would be 2 square root of x. But I'm not going to, well, I need to evaluate this at a location, and the location is the value 1, right? X equal 1. So here, if I let x equal 1, again, because of this up here, that's why x is equaling 1, this will be 1 over 2 square root 1, which is 1/2. All that for a measly little 1/2. Okay, got a 1/2 out of it. That's good news. I'm trying to find a slope of a tangent line so I can put it into this formula. So we already established that I was given that the y1 was 1 and that the x1 was 1. I just found that my slope was 1/2, and I can simplify this. So this is y equals 1, y minus 1 equals 1/2 x minus 1/2. I add my 1, negative 1/2 and positive 1 is positive 1/2. So this is y equals 1/2 x plus 1/2. It mentions on part B here that you can verify this with your graphing calculator. All it's telling you to do there is that you can put in this equation, and you can put in the original equation that you were given right here, and you can see that tangent line touching the graph as you expect. That's all it's talking about from part B, so I won't do that because that's just a matter of sticking things in your calculator. All right, so let me talk a little bit about what will be happening next time. I'm going to push pause on this.